So, welcome. I hope you all had a good Canada Day celebration. And today I'm going to be talking about multidimensional arrays in linear algebra and C++, but I wanted to present enough information that you can get going and you can just use it. And it is as simple as you think it is, basically, to use it. So let's get to that. And there's some examples in here, but more importantly, I discuss how you actually manipulate your multidimensional arrays. How do you go about using them, manipulating them? Because that's probably the most useful thing. The rest is just like calling functions. Okay, I am at the University of Windsor. So the Three Fires Confederacy of First Nations, that includes the Ojibwa, Odawa, and the Potawatomi. Uh, that is in the area I'm in, the University of Windsor and surrounding area. And don't forget that across the river, Detroit is part of this area. So uh, that belongs originally to those tribes. So this talk, multidimensional array accesses, of course, array slicing. So if you're used to doing that in other languages, how do you do it in C++? And can you do it efficiently? And the answer is yes. And of course, doing linear algebra. So now I arranged these slides. I'm going to talk about some preliminaries first. Always prefer using the latest stable compiler you can. And if you're using CPUs, use GCC or Clang. The Intel compiler you can use if you're using that on our clusters as well. I'm say prefer GCC and Slang because they are open source. So if you're using more than one computer, if you're using the GPUs and you're already doing CUDA stuff, great. You're probably going to prefer using the NVIDIA HPC SDK compiler, so NVC++. But regardless, try using the latest stable compiler that's released. But GCC, prefer using version 14 or later, Clang version 17 or newer for using like multidimensional arrays and linear algebra stuff. And basically, it's been released in the last couple years. Use it. Okay. And I should mention on Apple, which uses Clang, but they do their own Clang version. So version 16 or newer if you're using Apple's Xcode. Okay. So if you don't already know about it, I have it in these slides. If you go to cppreference.com, in my opinion, that's the best C++ online reference you'll find, period. Everything's in there. All the standards, what standards and what, whether it's been deprecated, removed, etc., when, all that, it's there. It's a very nice site. And it also has, not comprehensively, but has a lot of ISOC standard information as well. So, very useful site. And everything I'm talking about today can be done using existing implementations. You do not have to wait for a newer version of your compiler to come out with support for a newer standard. Okay, so I'm assuming if you're using this today, you're using this with these implementations. I should mention, just quick aside, the Microsoft Visual C++ compiler in Windows and the Clang compiler starting with, I think, version 18, implement MDSpan. The Clang compiler, though, actually, and I think the Microsoft one, don't implement sub-MDSpan, which is array slicing. So you might want to use these implementations even if your compiler already supports this stuff. So anyways, so the implementations to consider. If you're using the NVIDIA HPC SDK, you don't have to do anything else. MDSpan and the linear algebra stuff are, the multidimensional stuff and the linear algebra stuff are already in it. They have been since November 2022. If you need to use a different compiler or you want to use different environment and stuff like that, or maybe some backporting, MDSpan and sub-MDSpan can be used with the Cocos reference implementation that is there, and Cocos you don't install the whole Cocos project. That is just MDSpan. And then they have just linear algebra headers as well available. And you can use some older compilers as well with them because it's been backported. So if that is relevant, you can use those. Why use the NVIDIA HPC SDK? Well, you can use it for GPUs, yes. You can use the NVIDIA compiler and compile only for CPU as well. So if you don't have an NVIDIA card in your computer, but you install this compiler, you can use it as long as you tell it to compile only for CPU and not GPU. Things will work. In order for MDSpan and linear algebra to work, you have to put my apologies, -stdpar. You have to use that option. Okay. And if you're using on our clusters, module load NVHPC is all you have to do. Okay. The only thing you got to remember is the NVIDIA compiler uses round array brackets instead of square ones. So just use round array brackets. Okay. That's a thing. Eventually it'll change to the square ones, but that's what it is. If you want to compile for CPU only, put -stdpar equals multicore. And for GPU, -stdpar equals GPU. And make sure I would specify the C++23 option for the NVIDIA compiler. You'll get the most features that way. And if you're using the NVIDIA compiler, you can specify your architecture and your GPU architecture as well. And not at this very moment, but very soon, our clusters almost all the GPUs will be Hopper GPUs, so you can specify that and get the maximum performance by specifying that. Just add that to your command line. Now, if you're using one of the Cocos implementations, because you're using GCC or some other compiler, or the Intel compiler or Clang or whatever, you can do that, okay? You don't have to install the full Cocos implementation. So no panic there, okay? If you don't compile for benchmarks, don't compile the examples, and you don't compile the tests, in my experience, this appears to be completely header only, okay? So, I have the full instructions on how to build it in these slides, so you can see that. The important bit to remember that I encountered with the Cocos implementation of the linear algebra stuff is I found two things. One, I built the linear algebra stuff with C++20 support. This way you force, GCC supports the square brackets in C++23, but using square brackets for the linear and MDSpan stuff in the linear algebra implementation from Cocos has issues. You get compiler errors and all this stuff. So skip that. Compile for C++20 support, and then tell the Cocos library to use the parenthesis operator with setting that option when you build it, and happiness. And then you won't get a problem, even if you compile for C++23. Okay? And that way the parentheses can be just like the NVIDIA code using parentheses. Because the only compiler right now supporting square brackets is GCC. So unless that's your only compiler, it's nice if you can write your code that works with multiple compilers. So you might say, how do I install all this? Well, assuming you do everything from almost everything from first principles, but you install these two reference implementations from source code. You can just make an empty directory, cd into it, then you git clone Google test. If you are building tests, you need it. If you're not building any tests, this is not needed. So you git clone that, and then what do you do to build it? These commands will build it, and then you can get rid of your build directory for that. Then you do the same for MDSpan. Git clone MDSpan. Make a build directory for it, specify your options. I set most of these to off. The only thing I will point out that make sure you use C++20. So if you're using GCC, for example, I'm using GCC here, then this will cause the round bracket stuff to work. Additionally, I still specified use paren operator. Okay, the other thing I'll point out here is actually it's not in this. So you just choose the options you want. I guess if you want CUDA, you can say on, or if you were using HIP compiler from AMD stuff, then you can say on. But otherwise, if you say off, then it'll just have the code in it to do it. So try out your stuff, and then when you're done, make install, and it's header only, so you're just header files there. Similarly, you build the linear algebra library. Okay. Again, specify C++20 to avoid the square bracket issue, at least at this point. Turn everything else off. You might want to turn the BLAS on. So if you have Bliss or BLAS or like MKL or FlexiBLAS installed, all our clusters use FlexiBLAS and that's loaded by default, then you might want to say enable BLAS on. And that way for the routines that can be used in BLAS, it will use those. Okay, so you build it, great. And then when you're done, the only thing you have to do is compile your code telling it there's some additional include directories. So you just add -i, this include, and then the -i include /experimental into the directory where you installed it. Okay, remember to specify your libraries to link to, and again, if you're using our clusters to do stuff in parallel, and you're using the Cocoa stuff, remember the module load TBB threaded building blocks that's needed by GCC and the Intel compiler. And then you link with -l TPB. That's it. So I tried those out in dozens of ways. That'll work. Okay. So final and last detail of a preliminary. So you get all that built. You have it installed. Great, because you want to do real stuff. Okay, so now let's say for some reason on one computer or on our cluster you're using the NVIDIA compiler, and on your computer you're using GCC for some reason. You're using different things. Well, it's kind of silly to have slightly different beginnings of your programs based on how you want to pound include stuff and namespaces and all this, because unfortunately they're not the same. So what can you do? You can put them all in a header file. So let me show you how to do this. Okay, this is a complete header file. Okay, and I wrote it to be rather general. So if you pound include it and it can't include anything, then you'll just get an error message and that's it. Obviously, most people would prune this down somewhat, but what I do is I pound include mdspan if your system already supports it. I have a mistake in this header file. You should pound include version first. So, but you pound include mdspan, okay, and great. And I define a macro where the namespace is, and that's because the namespaces aren't the same in the other implementations. Okay, and since I included authentic mdspan, that means you must use square brackets. So I did the pound define mdspan uses standard mdspan. So if that macro is defined, you know you have to use square brackets. And you can do that in your code. Otherwise, include experimental mdspan, okay? And the namespace for it is this long thing. So I define mdspan namespace and put it there. So if you're using the standard one, then mdspan namespace is : standard. But if you're using the Cocos one, then it winds up being this : and whatever this macro is set to. Otherwise, use mdspan namespace standard experimental, which is where NVIDIA puts it. Okay, and if none of this works, output an error. You got to deal with that. And similarly, for linear algebra, if we can do it, linear algebra namespace standard linalg, the linear algebra stuff in the standard, which will be in the next standard, so C++ 26. That hasn't been approved yet. That should happen next year. We're on 3-year cycles. I'm on the standards committee, so when I say we, I'm one of those we that gets to vote on the standard. And linear algebra is it has its own namespace. So mdspan is in the standard namespace, but the linear algebra calls are in the linear algebra namespace. And that's because there's a lot of calls. So But again, MD span and the Cocos implementations have it in experimental slash linalg. So that's where it should be. And I do a linalg namespace because, you know, we get real complicated on the namespaces. And for NVIDIA, they put it in the standard experimental namespace. Okay, so there we have it. Why do all that? Why have a header file with all that? Well, because we can just then, you know, probably you're doing using namespace standard, fine. You can go using namespace MD namespace, semicolon, right? Say that. Or you can do specific symbol names like using linalg namespace colon colon matrix vector product, or you could go using namespace linalg namespace semicolon. So that makes your coding a lot easier, and you don't have to put standard colon colon etc. in front of things. Okay. So why do you want to use this MD span stuff? Enough of the preliminaries. Why do you want to use it? Okay. Manually calculating your multidimensional indices into your 1D arrays in C++ is horrible. It can be error prone, annoying. Sometimes it's hard if you got lots of indices. It can be inefficient, and it certainly can result in code that's hard to modify later. Why? Because you got all this I times j times this plus that, whatever. Okay, too much. Solution, MD span. MD, multi-dimensional span. If you're saying, is there such thing as a span? Yes, there is. I think it came in C++ 20. If I'm wrong, it's C++ 17. And that's for 1D arrays, okay? Contiguous arrays specifically. And it has iterator support and everything else. So that's really nice. But if you have multi-dimensional spans, what to use? Well, the solution is MD span, and it was voted into the C++ standard in C++ 23. So if you have the latest compiler tools, it's probably already in your compiler unless your compiler is GCC, because GCC hasn't put it in yet. Okay, the slides will be posted with the recording, so you'll have all the slides with the recording. So now why use MD span? Okay, you can map your contiguous 1D arrays to multiple dimensions. Number one. Yay! And you don't have to do all this I times the length of the row or this or that, realizing how it's stored or whatever and all that. Okay? Each dimension size can be specified with MD span. Okay? Multiple memory layouts are supported. So right now, that's row major and column major. There's one other one I won't mention. But with the next standard, there will be some additional layouts for some of the BLAS related items. Okay. Multiple access methods are also supported. So right now, it's just direct access. But if you wanted to have atomics or locks for what you're accessing, you'd be able to do that as well. So, enough of that. How would you go about using it? Okay, so you probably already have some sort of vector or object that holds your data. So, vector double, we'll just declare a vector double of n times m, and are integers, whatever size they are, okay? And I just want to fill my vector with it, okay? And then I make another vector of n times n elements, all doubles, and I'll call that out. Now, I'm going to create an MD span, okay, of n times m for A, that's the in vector, and B for the out vector, m times n. So m and n, you know, don't have to be the same size here. Then I might want to get all indices. So 0, 0, 0, 1, 0, 2, 0, 3, etc. I keep going through all my indices where it's row, comma, column. Well, how can I do that? Nice C++ 20 way of doing it is you can use the iota. If you're before C++ 20, use the iota standard algorithm and put that into a vector. But you can use the view, okay? for iota in the C++ 20 ranges, and you just do standard views, include ranges, and then standard views, and say iota, and you want to go from 0, just default construct to 0 here. So 0 to how big A's extent is. So that is M, because A is M by N, right? So A extent 0 is N, so this basically goes up to N. And then I go from 0 to M in the other iota view. So little a and little b here, okay? And then I do the Cartesian product of the two of them. So a and b here. Now I should mention that views in C++ ranges are lazy. They're not computed until you actually go through their elements, okay? So and I should mention they're also right now only sequential. So it's useful to see this. A lot of times it's very useful to do this, and it's not practical or even possible in some cases do it in parallel. So you just do it this way, and you get a nice easy way of doing all this. So I create a vector, okay, and I called it v2, and we go from the beginning to the end of v. And that's it. Just create a vector here. And what is this? V is my Cartesian product. So I need all my indices and row, comma, column, right? I want all my indices. Why do that? Because then I can use the C++ standard algorithm for each, passing in on line 21 here, execution power unsequenced. So we'll run this in parallel, unsequenced. Okay. Start at the beginning of V2, go to the end of V2. Okay, for parallel performance, you want to always use vectors on all implementations I've ever tried still. And C++20 ranges are still only sequential. That'll change in the future, but that's what it is right now. So for each, what do I want to do each time? I want to just compute the transpose of my two matrices. So B, j, I equals A, I, j. And if you're using the NVIDIA compiler or the round bracket way of doing it with the Cocos implementations, just switch the square brackets here to round brackets. This line 26 is the only multidimensional array access. Okay, and my index, this here, if you haven't seen it before, this syntax, if you have a tuple, so standard pair, tuple, or standard array of n indices, or n values, you can just go auto, because the compiler knows the type. You can just go auto ref or something like that, or auto const ref if you want. Put square bracket, and then just put the variable names you want to use for each value in the tuple. Okay, so the I will be the first one, j will be the second one. So I will be the row, j will be the column. So a, I, j. B equals, and B, assign that to B, j, I. So that's the transpose. So this will do a parallel transpose. Obviously, maybe not the most efficient thing, but you can do it. Okay, so that gives you an idea here how to use it. Important piece to know. MD-span is extremely lightweight. Extremely lightweight. So just create them by value, pass them by value. Don't worry about passing them by reference or anything. However, they refer to the memory you're using. So the memory's got to exist somewhere. So you need to hold them in something. So whether that's vectors or whatever it is you're using, hold them in some object. The memory comes from somewhere else. With vector.data returns a pointer. Remember, these are for contiguous arrays. So you just pass the pointer in, you're good. Now, for simplicity of presentation here, MD-span, I did not put any template arguments for MD-span. I put the runtime extents here, and using C++, it's able to figure out, won't go into details, the compiler can figure out the settings needed for MD-span. Okay, for the template parameters. But normally you would want to put them, and I'm going to explain that in a bit. Okay, down here, if you're wondering how vector is used without template parameters, it's the same thing. It's able to determine from the input to the constructor what the template parameter must be. In this case, double, because this sorry, this is not a double. This is a Cartesian product of pairs of integers. So it's a tuple of size t comma size t. And so it figures that out. I like it when I don't have to figure it out, except when I'm doing a presentation talking about it. Okay. So anyways, that's how you can go about using it. So if you pound include it, you can use it like that. So what is MD-span? Okay, well, you say what type you want. If you're giving the template arguments, you say what type you want in it. So you're having a multi-dimensional thing, and I have doubles. So the first parameter would need doubles. Okay, great. The second parameter, which is also required, is the extents. How big is each dimension? And it supports static and dynamic extensions. Okay, the third argument, which defaults to the way of storing things that C and C++ do in memory. Okay, that's a row major order. Layout right is the default. Layout left is supported, and that is for Fortran layout. Accessor policy, the default accessor just directly accesses the memory. However, as I said before, it could grab a lock or use an atomic, or I guess somebody will write at some point something to use MPI, PGAS stuff that's across the cluster or whatever. That doesn't exist yet, but at some point. Now, MD spans are views. They're very small in size, fast to copy. They have reference semantics. They don't own the data they point to. You basically give it a pointer and it runs away with the pointer. There's no iterators available for MD span, not yet, okay? And understand they're not containers. They're just views, okay? Now, the second parameter is normally an instance of standard extents, okay? And what is that? That's you telling it how many dimensions and how big each dimension is. And if you don't know, because it's dynamic, you just say standard dynamic extent, okay? If you know all dimensions at runtime only, there's a shortcut, you can say standard d extents to do it. If you're doing a using namespace thing, you can get rid of the standard colon, especially if you're using the implementations. Okay. Now, some examples. Suppose you want 5 by 3 by 15. That's your dimensions. 5, 3, and 15. That's how big they are. Well, you would just write extents size t. Typically, size t is an unsigned integer. 5, 3, 15. Done. Okay. So your vector would be, if you're holding everything in a vector, would be 5 times 3 times 15 elements. Okay. But let's say for some reason you didn't know the size of the middle one, the 3. You didn't know that until runtime. It could be something different. Okay. What can you do? You can say, oh, the extents are 5, dynamic extent 15. And then you have to tell it at runtime what it is. So when you make your MD span, this is what it would look like. And notice here you pass in some pointer, comma 3. You have to tell it the first, all your dynamic extents, you have to tell it all of them at runtime. You have to pass it in. Okay. And similarly, if you have 5 by I don't know, so it's 3-dimensional, but I don't know how big the last 2 are, no problem. Just say 5 dynamic extent, and then notice here when you say your extents, dynamic, and then you have to give the 3 and the 15 here. That can be handy because let's say you don't know till runtime how big everything is. Well, there you go. And if you had to do it with all of them, great, you could just put dynamic extent in all of them and just pass your values in. But if you have to do all of them, I did say you could just pass in d extent size t3, and then you could just pass your value. So instead of this long thing with a bunch of dynamic extents, you can just go d extent size t3. Okay, so that's the second parameter. The third parameter, you got 3 choices unless you're writing your own. The layout right, which is the default. Layout left, if you are interacting with Fortran code, that's layout left. Layout stride lets you specify all the strides manually. Okay. Probably not using that unless you're doing something very special. Okay. There's one accessor type, unless you write your own, and default accessors directly access things. And again, why have accessors? It's It's simply so you can grab a lock or do an atomic, or if you're doing parallel things with MPI and all that stuff and arrays and stuff like that, and you need to do something special to access each one. Okay, so you might say, great, I can get a multi-dimensional array. I get that. Instead of putting square bracket, some index, square bracket, close, square bracket, open, some index, square bracket, close, and doing all that kind of stuff, and having issues with that, I can just put everything, I, comma, j, comma, k, comma, whatever, keep going. Great, no problem. So you'll say, but I don't normally want to do that. Like sometimes I want to get a row of my matrix or get a column of my matrix. What can you do? Well, there's a function called sub-MD-span. Okay, now that'll come in the next standard. It just missed the window to go into C++23. So it was literally put into the next standard. So all the implementations provide it though. But sub-MD spans let you get slices of your multi-dimensional spans. So if you want a column or whatever, so what is it? So I have some MD span called matrix because it's two-dimensional. You might say, how can I insist it's two-dimensional? Look at this line 2, line 8's the same. I just say its rank. If its rank is 2, okay, then it's two-dimensional. Okay, so return sub-MD span. I pass in my MD span variable. Okay, and then I have one value for each dimension that's relevant for the sub-MD span. And if I go I, comma, full extent, then I want to get row I, because I'm row by column, so row is the first one, column's the second one, so row I, and then all the values in the columns. So I is fixed, but all the values in the columns. So this decreases my rank by 1, right? I'm getting a row back. And here I'm doing the opposite column. If column is the second one here, then full extent, comma I, where I is the value I pass in. That's it. That's my slice. So is it uglier than other shortcuts in other programming languages? Sure. It's uglier, but you can do it now, and it's very efficient. Let's see one more example. We're not going to do the full-blown implementation, but let's just see the sub-MD spans being used to do something fancier. Okay, suppose you might have read about Strasson's matrix multiplication algorithm, which works for square matrices that are powers of 2. They're powers of 2 because you keep dividing them in half each time. Why? Because if you have some matrix A, you go A11, A12, A21, A22. So you make sub-matrices from A, where these are also square, ideally, right? They want them all the same size. So you get A, B, C, and they're also square, and you keep subdividing them and subdividing, okay? And you'll say, well, how do I subdivide them? I don't want to copy all the values. I just want A, B, and C, okay? Well, Strasson's algorithm does the matrix operations with these intermediate values, which I'm not going to get into, but if you're curious, look it up. You can see them, but notice here I use A11 and A22 and B11 and all this stuff. I use all these values, okay? Now, what you need in this algorithm is you want to get A11, A12, A21, A22, etc. You want to get all of those things, all of these here. You want to get all of these things. Okay, how do you get them? Well, nicely, all of them are exactly the same size, so I only have to use the size of A. So what do? If I take A's index type, so that'll be some type of integer, probably size t, but anyways, this will do that. Okay, then I want a tuple of that index type, right? Because these are two-dimensional. Okay, so if I construct my lower one from the index type to, remember they're the same size, so the index type up to but not including the size of that dimension divided by 2, and remember they're the same size, so I just have to use the first one, and then upper goes from half that size of that dimension divided by 2 up to but not including the actual size. Okay, so lower and upper there. Then I get all those sub-matrices like this. A11 is sub-MD span, A lower upper. or lower, sorry. A12 is a lower upper. A21 is a upper lower. A22 is upper upper. Go through the list. And I didn't mention already, this MD span stuff works on GPU code. So if you're doing CUDA code and you're doing all this stuff and you pass in a pointer to your kernel and you want to use MD span so you don't have to do all the multidimensional stuff yourself, no problem. Use it. It's already there in the NVIDIA compiler. You can use the MD span stuff with existing CUDA code as well. You just don't, it's not just standard power. So anyways, you use this and now you can do the rest because you can pass these submatrices into the linear algebra routines or whatever else you got to do with them. Anyways, we don't want to do the actual full-blown algorithm. So how can you do all these slices? Well, you can pass in an integral value. You saw that. I showed you how I could get a row or a column of a matrix. Okay. Or of an MD span, but really they're all matrices and vectors and points and stuff like that. Okay, I can have a type convertible to a tuple, you know, of MD span index type or index type. If you have more than one dimension, then just as a tuple of number of dimensions. Okay, it's half open. Okay, so you go start stop. Okay, strided slice. Okay, it is start, extent or size, then the stride. That's important. My next slide will talk about that. Or you say the full extent if you just want to use all of them. Okay. Why is that start, size, stride important? It's different from what you're used to in Fortran, NumPy, MATLAB, etc. Okay. In Fortran, it's start, stop, step. NumPy, it's start, stop, step. In MATLAB, it's start, step, stop. Same thing, but just slightly different order. Okay. But in C++, it's equivalent to start, stop minus start, step. And if you're wondering why, it's because it is more efficient to do it that way. There are some compile time specified things that combined with a runtime value still lead to compile time performance. So that is why C++ does it this way. So if you are copying existing Fortran, NumPy, or MATLAB code into C++, remember that the second value will be different. It's not the stop, it's the size. So really it's stop minus start. Okay, if you're using sub-MD span, okay, so I got a little bit of code here. I have a vector, now obviously a real small vector here. Okay, 10 doubles. They're all zeros here. And then I fill them all in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. No problem with iota. Okay. And then I make an MD span. There's only one dimension of 10 values. So I assert the rank as 1. Okay. So sub MD span. If I ask for the fifth element, right? Because it starts at 0. Remember, everything starts at 0 in C++. So we get a 0D result. It does work with that. MD span supports 0 dimensions. Okay, that means effectively your array brackets are empty. The rank will be 0. And if you access that, it'll give you 1 value. Okay, it's equivalent to accessing the MD span M with 4. Okay, but it's all offset to the view of it. Sub MD span just returns another MD span that looks like it's the whole thing, but it isn't, of course. Okay, so you might say, well, what is this tuple thing? 2, well, 2 to 5, 2, 3, 4 is the values. And as you see here, 2, 3, and 4. So if I do sub MD span with 2 to 5 for M, given what M is up here, then I can see my sub MD span, MD span here, 0, 1, 2 will give me 2, 3, 4, which is exactly what I want. And the extent of it is 3 and it's rank 1. That's how the tuple works. Strided slice, same thing, but remember it starts size and then step. Okay, so because I said size is 7, okay, 3 here, but size is the full length of it. of the dimension. Okay, so here we go. That'll give you that. So if you have to do the stepping thing, that's how you do it. And finally, if you have to say everything because you want it to be the same, then this will do it. But you'll say those are only 1D. How do you do 2D? Well, this will show you how to do the 2D. And I simplified here saying, look, this is equal to the matrix I comma 3 because we said full extent comma 3. Okay, similarly, strided slice, 0 full extent, and you can do stuff like this. Okay, so have fun, do it, whatever you got to do. Okay, so now, what about linear algebra? Okay, no problem. It's very likely to have this in it. C++ 26 doesn't exist yet. Next year. Okay, now you don't have to wait. It's already in the implementations that I mentioned. Okay, so BLAST 1, 2, and 3 are there. Okay, and it's easy to use them. You just call them. That's it, you call them. So you know what they are, you call them. And if you pass in as the first argument, just like C++ parallel algorithms, one of the unsequenced par unsequenced, I don't think anyone bothers with sequential, the SEQ, that will run it in parallel appropriately. Okay, and what you do is you pass the linear algebra library MD spans instead of vectors and points and matrices and tensors or whatever. Okay, BLAST 1, 2, and 3 supports the scalars are all like your doubles and floats and stuff like that. The 1D entities will be MD spans and 2D entities will be MD spans. BLAST 3 supports matrix operations. So if you're doing more than that, then you'll need to do slices. You might say, oh, I know BLAST. What does it support? Well, all of these routines are implemented where the small x is, S for single precision, D for double precision, C for complex, that kind of thing. So X just stands for the type there. In C++, everything's templated, so you don't have to specify all that. And these names are not the ones used. So I have a bunch of slides in the appendices that go through them. But you can see here a whole bunch of routines are supported. This is most of them, not all of them, but most of them. You got your symmetric matrices in there, and you got your Hermitian ones as well. Okay, your rotates and things like this. There is one LePac routine implemented. I should say routines, but single, double, etc. Same diff in C++. So when you're using templates, so LePac, this one is implemented. And there are some routines mentioned in the BLAST standard, but are not formally there, and they are implemented. So the Frobenius norm, one norm, and infinity norm are also in there. Now, I just mentioned their names because it's good enough to know they're there. My slides have their actual names. And the references refer to the document that gives all the details for them as well. So either way, but you might say, okay, how can I say I want to print out a two-dimensional MD span? Whatever. Normally we call these matrices, right? Row I call them, but whatever. It's an MD span. It's a multi-dimensional span. Well, all I have to do is pass it in. I can say requires T : rank is 2. So that means the rank has to be 2. Okay. And you can put more requirements if you want, but that basically says this routine is going to work with two-dimensional stuff. Great. And T should be an MD span, right? So now I can have my for loops for I and for J. And look at this, extent 0 and extent 1. And I know it's two-dimensional because I just required it up here. So this routine's only being used with two-dimensional MD spans. Great. So then I can do it, and I put round brackets this time, but Mij is accessing the I comma j element. You could have Mij equals and assign it a value. Here I'm just printing out values. Okay. Calling such is straightforward. Okay. So I need to store my values somewhere. Remember, that's not included. MDSpan is just takes a pointer. So wherever it points to, it has to be somewhere else. Okay, so I'll declare some vectors, fill them with some values. Iota goes from 0, because I pass in 0, 1, 2, 3, 4, 5, all the way up to the highest. 4 times 3 is 12, so 0 to 11 here. Okay, 3 times 7 is 21, so this will go from 0 to 20. Okay, then I have my MD spans of it. So AM is the MD span of A, BM is the MD span of B. Some of you might say, hey, can we have more than one MD span on the same array to give it a different view? Yes, you can. Some languages call that reshaping. So if you have a need to reshape your matrix to look different, you can do that. Okay, just declare another MD span. So you can see the dimensions here though. I don't have to worry about the actual sizes and all that other stuff. And I can print them out with that routine I just showed you. So lines 4, 5, and 10 here, print out them. Awesome. So if I make C, which should be 4 times 7 elements, because I'm multiplying the two of these, this is what I can do. And matrix product is one of those routines. And I pass in execution power, and it's A times B, put the result in C. Okay, so that's it. That's all I have to do. So if I have a using namespace and the stuff and all that already done, standard and all the namespaces I need, then this code will do it. So if you have linear algebra code, great. Have at it. Now I'll just point out to you, I do have my bibliography does give where all these things are on the web, okay, and referred to in the slides. But here, just show you in the appendices, I have BLAS 1, 2, and 3, and it goes through giving you all the routines, their names. Here, I'll show you a different one. We go to a common one. A lot of things on the web like to show you SAXP or DAXP. Well, what is that? In the BLAS library, it's add. So if you call linspace : add, and then you pass in your input object, and these two input objects, okay, there'll be one dimension, and then your output object, where you want the data to be written to, also needs to be one dimension, then it'll do SAXP for you. And if you pass in an execution policy, it'll do that for you. And I didn't really mention, if you pass in standard par with the NVIDIA compiler and you're using the GPU, this will compile and run on the GPU if you're using an execution policy that it supports, which is par unsequenced, and the newer compilers support par as well for the NVIDIA compilers. For if you're using the other implementation, par underscore unsequenced, when you're using GPUs is normally the one that's supported. So anyways, that's it. I will open it back up to questions.